Hello everyone, my name is Laszlo Molnar. Today I will present our research about AI in high school physics education. I am a teacher of mathematics, physics and computer science at the Gymnasium of Pilakovo and also a PhD student at Eötvös Loránd University in Budapest. The rapid spread of artificial intelligence greatly affects students and becomes part of their daily lives. School must keep up with this trend. There is a strong expectation from society for schools to introduce AI and prepare students to use it. We know that using AI effectively at work is also becoming a common requirement. Unplanned and unprepared use in schools can lead students down the wrong path. The goal is not for students to see AI as an all-knowing perfect servant that gives instant answers, because this does not help their growth. Instead, students need to learn that AI is a helpful partner that supports their development and helps them solve problems and tasks effectively. When using artificial intelligence in the classroom, the learning process can easily go off track without proper guidance. With unguided AI use, students get used to not thinking because they receive instant answers, assuming they are always correct without double-checking, and they often use sources that do not align with the curriculum or their prior knowledge. In contrast, guided classroom AI use offers key advantages. The teacher defines the learning scenario, sources are carefully selected and aligned with the curriculum. The AI guides students through questions instead of shortcuts. Data from pre- and post-tests helps inform future teaching decisions. From a research perspective, AI use becomes clear and comparable. The graph effect can be interpreted more responsibly, and teacher remains fully accountable for learning design. In this section, I will present our methodology for governed AI learning scenario. Our target group consists of high school students attending physics classes. For the AI infrastructure, we use the Gemini Notebook-LM environment with teacher-selected, curriculum-aligned materials. We set strict governance rules so the AI would avoid giving direct answers and instead guide students with reflective questions. Pedagogically, the AI served as a Socratic learning partner, while the assessment and overall responsibility remained with the teacher. We can divide the students' reactions into two main groups. The first group shows a bad habit. They expect AI to give immediate answers, which they accept blindly because they believe AI is much smarter. These students felt frustrated and upset when using our special system where the AI asks questions back. The second group shows a good habit, or simply had less prior experience with AI. After an initial surprise, they enjoyed working with the system. They accepted that AI is a helper, but it cannot replace their own critical thinking. The goal of our research is to examine how AI can be integrated into high school physics education. We investigated whether we can reduce the performance gap between students with different preparation levels and abilities. Today, I would like to present these results to you. It is clear that using AI supports personalized learning speeds and individual progress, as students can work with content that matches different learning styles. Finally, our research aims to see if using AI in the classroom improves student motivation and long-term performance. Now I would like to explain our work methodology. We divided the students into two main groups. The control group used traditional textbooks for learning. The experimental group used Gemini Notebook for interactive learning. Both groups followed the same lesson workflow. We started with a short teacher-guided motivational introduction. After that, the students worked independently. To measure their progress, students completed pre-test and post-test on their phones or computers with no external help allowed. For our digital infrastructure, we relied on Google Workspace for Education and ASC Agenda. On this slide, we focus on custom gems used as governed learning partners. We customized both the AI's behavior and its knowledge sources by using teacher-selected materials and setting explicit interaction rules. We developed two distinct gems for classroom use. Gem 1 acts as Socratic problem-solving guide, assisting physics students step by step while avoiding final numerical answers and asking reflective questions. Gem 2 serves as a formative assessment partner, asking conceptual questions, evaluating student responses, providing immediate feedback, and generating summary reports for teacher interpretation. The biggest challenge was saving the full conversation in text format. The AI proved to be very unreliable and cumbersome during this process. We did not use AI as an open chatbot. We built it directly into our lessons. The process has three simple steps. First, before class, the teacher selects the topic, sources, and tests. Second, during class, the AI asks questions while the teacher monitors the students. Third, after class, we look at the test data to see what worked and improve our next lesson. We aim to integrate the use of artificial intelligence into every type of physics task. During the study, students had to solve several types of tasks: learning new material, analyzing video measurements, conducting laboratory measurements, comprehensive reviews. First, I would like to present the aggregated results. The graph shows the percentage point differences between students' pre-test and post-test scores, grouped by their initial level of preparation and ability. In these overall results, we did not make a distinction between the test group and the control group. In our analysis, students with lower initial preparation achieved a larger jump in test scores. High-performing students maintained their high scores, but showed a smaller numerical increase compared to their already high pre-test scores. Before starting the lesson, both the experimental and control groups were at the same knowledge level. Their pre-test scores showed no significant difference. Looking at overall progress, students in both groups improved significantly from pre-test to post-test. On average, the overall learning gains were very similar between the two teaching methods. However, breaking the data down to subgroups reveals a crucial pattern. The AI-supported approach benefited lower and average achieving students much more than top performers. A working hypothesis was that properly structured AI support might help reduce the learning gap between students of different performance levels. The subgroup level results suggest that hypothesis showing that governed AI support was especially beneficial for lower and average achieving students. For high performers, there was only a minimal AI advantage, and textbook-based learning was actually slightly more efficient for the top 90% to 100% group. In conclusion, AI support must be differentiated. For lower performers benefit from guided scaffolding, while high performers need concise high-density materials. Learning data helps teachers decide how AI support should be structured, limited, or intensified. The process begins with gathering prior data from pretest and past achievement, which allows the teacher to group students and identify their specific support needs. Next, a governed AI scenario is introduced, acting as a Socratic guide or an assessment partner. Throughout the lesson, the teacher monitors the class to observe confusion, over-reliance, or progress. Based on these insights, the teacher makes the next decision to adjust AI use, offer traditional support, or change the pacing. Ultimately, classroom AI should not be applied uniformly. Its role must adapt to prior achievement, learning behavior, and measured progress, which explains why overall average result often mask meaningful subgroup effects. We asked students to compare the textbook with Gemini Notebook. Lower performing students loved the interactive support. Flashcards and study guides kept them focused and made learning easier. High performing students preferred simple, direct textbook formulas. Too many AI tools felt distracting for them. The key teaching implication is that AI must be governed and adopted differently depending on each student's learning profile. To summarize, AI works best as a guided learning partner, not an answer machine. The teacher remains in full control. The teacher sets goals, picks sources, and makes final decisions. Lower and average performing students gained the most from this method. High performers need more direct, concise materials. Good AI use needs both smart teaching design and clear data management. Let me address our limitations and next steps. First, our study was short. It only measured immediate learning in single lessons. We cannot claim long-term grade improvements yet. Next year, we will track students for a full semester. We will also compare planned versus spontaneous AI use. Finally, we will refine our model for journal publication. Thank you very much for your time and attention today. I hope this presentation provided clear insights into our findings and approach. If you have any questions, comments, please feel free to reach out to me.